Welcome friends, in this session we discuss the sequences of real numbers part 4. A subsequence is a sequence that can be derived from another sequence by deleting some elements without changing the order of the remaining elements. In this session we introduce the notion of a subsequence of a sequence of real numbers. This notion is somewhat more general than that of a tail of a sequence and is often useful in establishing the divergence of a sequence. By Bolzano-Weierstrass theorem, we will see that a bounded sequence of real numbers has a convergent subsequence. We will give two proofs for Bolzano-Weierstrass theorem. One of them is based on nested interval property. Subsequences. Definition: let x equal to sequence x n be a sequence of real numbers, then any infinite succession of its terms picked out in any way but preserving the original order is called a subsequence of the sequence x n. Let n1 less than n2 less than etc. less than nk less than etc. be a strictly increasing sequence of natural numbers, then the sequence x dash equal to sequence x n k in R given by sequence x n1, x n2, x n3 etc. x n k etc. is a subsequence of x. For example, the following are subsequences of x equal to sequence 1 by 1, 1 by 2, 1 by 3 etc. 1 by 3, 1 by 4, 1 by 5 etc. 1 by n plus 2 etc. 1 by 1, 1 by 3, 1 by 5 etc. 1 by 2n minus 1 etc. 1 by 2 factorial, 1 by 4 factorial etc. 1 by 2n factorial etc. The following sequences are not subsequences of x equal to sequence 1 by n. Sequence 1 by 2, 1 by 4, 1 by 6, 1 by 1, 1 by 3, 1 by 5 etc. Sequence 1 by 1, 2, 1 by 3, 4, 1 by 5, 6 etc. Of course, any tail of a sequence is a subsequence. In fact, the m tail corresponds to the sequence of indices n1 equal to m plus 1, n2 equal to m plus 2 etc. nk equal to m plus k etc. However, not every subsequence of a given sequence need not be a tail of the sequence. Convergence of subsequences of converging sequences. We now show that subsequences of convergent sequences also converge to the same limit. Theorem 1. If a sequence x equal to sequence x n of real numbers converges to a real number x, then any subsequence of x also converges to x. Proof. Let epsilon greater than 0 be given and let k of epsilon be such that if n greater than or equal to k of epsilon, then modulus of x n minus x less than epsilon. Since n1 less than n2 less than etc. less than nk less than etc. is an increasing sequence of natural numbers, it can be proved by induction that nk greater than or equal to n. Hence, if k greater than or equal to k of epsilon, then nk greater than or equal to k greater than or equal to k of epsilon, so that modulus of x n k minus x less than epsilon. Therefore, the subsequence x n k also converges to x. This completes the proof. Example 1. Limit sequence r raised to n equal to 0 if 0 less than r less than 1. Solution. Take x n equal to r raised to n. Since 0 less than r less than 1, then x n plus 1 equal to r raised to n plus 1 less than r raised to n equal to x n, so that the sequence x n is decreasing. It is also clear that 0 less than or equal to x n less than or equal to 1. So, it follows from the monotone convergence theorem that the sequence is convergent. Let x equal to limit sequence x n. Since sequence x to n is a subsequence of x n, it follows from the previous theorem that x equal to limit sequence x to n. On the other hand, it follows from the relation x to n equal to r raised to 2n equal to r raised to n square equal to x n square, that x equal to limit sequence x to n equal to limit sequence x n square equal to x square. Hence, x square minus x equal to 0, that is x into x minus 1 equal to 0. Therefore, we must have either x equal to 0 or x equal to 1. Since the sequence x n is decreasing and bounded above by r less than 1, we deduce that x equal to 0. Example 2. Limit sequence a raised to 1 by n equal to 1 for a greater than 1. Solution. Since a greater than 1, note that if Zn equal to a raised to 1 by n, then Zn greater than 1 and Zn plus 1 less than Zn for all n belongs to n. Thus, by the monotone convergence theorem, the limit z equal to limit sequence z n exists. Hence, by theorem 1, it follows that z equal to sequence z 2n. On the other hand, it follows from the relation z 2n equal to a raised to 1 by 2n equal to a raised to 1 by n raised to 1 by 2 equal to z n raised to 1 by 2. That z equal to limit sequence z 2n equal to limit z n raised to 1 by 2 equal to z raised to 1 by 2. Therefore, we have z square equal to z, whence it follows that either z equal to 0 or z equal to 1. Since z n greater than 1 for all n belongs to n, we deduce that z equal to 1. The use of subsequences makes it easy to provide a test for the divergence of a sequence. Theorem 2, divergence criterion. Let x equal to sequence x n be a sequence of real numbers, then the following statements are equivalent. 1. The sequence x equal to sequence x n does not converge to x belongs to R. 2. There exists an epsilon naught greater than 0 such that for any k belongs to n, there exists n k belongs to n such that n k greater than or equal to k and modulus of x n k minus x is greater than or equal to epsilon naught. 3. There exists an epsilon naught greater than 0 and a subsequence x dash is equal to sequence x n k of x such that modulus of x n k minus x greater than or equal to epsilon naught for all k belongs to n. Proof. 1 implies 2 if x equal to x n does not converge to x, then for some epsilon naught greater than 0 it is impossible to find a natural number k of epsilon such that for all n greater than or equal to k of epsilon the terms x n satisfy modulus of x n minus x less than epsilon holds. That is, for each k belongs to n, it is not true that for all n greater than or equal to k, the inequality modulus of x n minus x less than epsilon naught holds. In other words, for every k belongs to n, there exists a natural number n k greater than or equal to k such that modulus of x n k minus x greater than or equal to epsilon naught. 2 implies 3. Let epsilon naught be a sin 2 and let n 1 belongs to n be such that n 1 greater than or equal to 1 and modulus of x n 1 minus x greater than or equal to epsilon naught. Now, let n 2 belongs to n be such that n 2 greater than n 1 and modulus of x n 2 minus x greater than or equal to epsilon naught. Let n 3 belongs to n be such that n 3 greater than n 2 and modulus of x n 3 minus x greater than or equal to epsilon naught. Continuing in this way, we obtain a subsequence x dash is equal to sequence x n k of x such that modulus of x n k minus x greater than or equal to epsilon naught for all k belongs to n. 3 implies 1. Suppose x equal to x n has a subsequence x dash is equal to sequence x n k satisfying the condition in 3, then x cannot converge to x. For if it did, then by theorem 1 the subsequence x dash would also converge to x, but this is impossible since none of the terms of x dash belongs to the epsilon naught neighborhood of x. This completes the proof. Since all the subsequences of a convergent sequence must converge to the same limit, we have part 1 in the following result. Part 2 follows from the fact that a convergent sequence is bounded. Divergence criteria. If a sequence x equal to sequence x n of real numbers has either of the following properties, then x is divergent. 1. X has two convergent subsequences, x dash is equal to sequence x n k and x double dash is equal to sequence x r k whose limits are not equal. 2. X is unbounded. Example 3. Show that the sequence 1 1 by 2 3 1 by 4 etc. is divergent. Argument 1. The given is the sequence y equal to sequence y n, where y n equal to n if n is odd, 1 by n if n is even. It can easily be seen that the sequence is not bounded, hence it cannot be convergent. Argument 2. We notice that although a subsequence 1 by 2, 1 by 4, 1 by 6 etc. of y converges to 0, the entire sequence y does not converge to 0. Indeed, there is a subsequence 3, 5, 7 etc. of y that remains outside the 1 neighborhood of 0. Hence, y does not converge to 0. Example 4. Show that the sequence minus 1 raised to n is divergent. Solution. If the sequence x equal to sequence minus 1 raised to n were convergent to a number x, then every subsequence of x must converge to x. Since there is a subsequence x dash is equal to 1 1 1 etc. converging to plus 1 and another subsequence x double dash is equal to minus 1 minus 1 minus 1 etc. converging to minus 1. By divergence criteria, we conclude that x must be divergent. Example 5. The sequence S is equal to sequence sin n is divergent. Solution. We recall that sin pi by 6 equal to 1 by 2 equal to sin 5 pi by 6 and that sin x greater than 1 by 2 for x in the interval I1 equal to pi by 6 5 pi by 6. Since the length of I1 is 5 pi by 6 minus pi by 6 equal to 2 pi by 3 greater than 2, there are at least 2 natural numbers lying inside I1. We let n1 be the first such number. Similarly, for each k belongs to n, sin x greater than 1 by 2 for x in the interval ik equal to pi by 6 plus 2 pi into k minus 1, 5 pi by 6 plus 2 pi into k minus 1. Since the length of ik is greater than 2, there are at least 2 natural numbers lying inside ik. We let nk be the first one. The subsequence s dash is equal to sequence sin nk of s obtained in this way has the property that all of its values lie in the interval closed interval 1 by 2 1. Similarly, if k belongs to n and jk is the interval, jk is equal to open interval 7 pi by 6 plus 2 pi into k minus 1, 11 pi by 6 plus 2 pi into k minus 1. Then it is seen that sin x less than minus 1 by 2 for all x belongs to jk and the length of jk is greater than 2. Let mk be the first natural number lying jk. Then the subsequence s double dash is equal to sequence sin mk of s has the property that all of its values lies in the interval minus 1 minus 1 by 2. Given any real number a, it is readily seen that at least one of the subsequences s dash and s double dash lies entirely outside of the 1 by 2 neighborhood of a. Therefore, a cannot be a limit of s. Since a belongs to R is arbitrary, we deduce that s is divergent. The existence of monotone subsequences. We now show that every sequence has a monotone subsequence. Theorem 3. Monotone subsequence theorem. If x equal to sequence x n is a sequence of real numbers, then there is a subsequence of x that is monotone. Proof. For the purpose of this proof, we will say that the mth term x m is a peak if x m greater than or equal to x n for all n belongs to n with m less than or equal to n. That is, x m is never exceeded by any term that follows it in the sequence. We will consider two cases depending on whether x has infinitely many or finitely many peaks. Case 1. X has infinitely many peaks. In this case, we order the peaks by increasing subscripts. Thus, we have the peaks x m1, x m2, etc., x mk, etc., where m1 less than m2 less than etc. less than mk less than etc. Since each of the term is a peak, we have x m1 greater than or equal to x m2 greater than or equal to etc. greater than or equal to x mk greater than or equal to etc. Hence, the subsequence x mk of peaks is a decreasing subsequence of x. Case 2. X has finite number, possibly 0, of peaks. Let these peaks be x m1, x m2, etc., x mr. Let S1 equal to mr plus 1, the first index beyond the last peak. Since x S1 is not a peak, there exists S2 greater than S1 such that x S1 less than x S2. Since x S2 is not a peak, there exists S3 greater than S2 such that x S2 less than x S3. If we continue in this manner, we obtain an increasing subsequence x Sn of x. This completes the proof. Remark. It is not difficult to see that a given subsequence may have one subsequence that is increasing and another subsequence that is decreasing. The Bolzano-Weierstrass theorem. We will now use the monotone subsequence theorem to prove the Bolzano-Weierstrass theorem. which states that every bounded sequence has a convergent subsequence. Theorem 4. The Bolzano-Weierstrass theorem. A bounded sequence of real numbers has a convergent subsequence. Proof. It follows from the monotone subsequence theorem that if x equal to sequence xn is a bounded sequence, then it has a subsequence x dash is equal to sequence xnk, that is monotone. Since this subsequence is also bounded, it follows from the monotone convergence theorem that the subsequence is convergent. We also give a second proof of Bolzano-Weierstrass theorem. It is based on the nested interval property. For that purpose, we describe the definition of nested intervals and nested interval property. Definition. A sequence of intervals n belongs to n is nested if the following chain of inclusions holds: I1 superset of I2, superset of I3, superset etc., superset of In, superset of In plus 1, superset etc. See figure 1. Example 6. If In equal to closed interval 0 1 by n belongs to n, then In superset of In plus 1 for each n belongs to n, so that the sequence of intervals is nested. In this case, the element 0 belongs to all In, and using Archimedean property, it can be proved that 0 is the only such element. Hence, intersection n equal to 1 to infinity In equal to 0. There are nested sequences of intervals that need not have a common point. For example, the sequence of intervals kn equal to n infinity n belongs to n is nested, but has no common point. However, the following result says that every nested sequence of closed and bounded intervals does have a common point. Theorem 2. Nested interval property. If In equal to closed interval an bn n belongs to n is a nested sequence of closed and bounded intervals, then there exists a number psi belongs to R such that psi belongs to In for all n belongs to n. Proof. Since the intervals are nested, we have In contained in I1 for all n belongs to n, so that an less than or equal to b1 for all n belongs to n. Hence, the non-empty set n belongs to n is bounded above. Hence, by the supremum property of R, supremum of the set exists. We let psi be the supremum. Clearly, an less than or equal to psi for all n belongs to n. We claim also that psi less than or equal to bn for all n. This is established by showing that for any particular n, the number bn is an upper bound for the set ak k belongs to n. We consider two cases. 1. If n less than or equal to k, then since In superset of ik, we have ak less than or equal to bk less than or equal to bn. 2. If k less than n, then since ik superset of In, we have ak less than or equal to an less than or equal to bn. See figure 2. Thus, we conclude that ak less than or equal to bn for all k, so that bn is an upper bound of the set ak k belongs to n. Hence, psi less than or equal to bn for each n belongs to n. Since an less than or equal to psi less than or equal to bn for all n, we have psi belongs to In for all n belongs to n. Proof of Bolzano-Weierstrass theorem using nested interval property. Since the set of values xn n belongs to n is bounded, this set is contained in an interval I1 equal to closed interval a b. We take n1 equal to 1. We now bisect I1 into two equal subintervals I1 dash and I1 double dash, and divide the set of indices n belongs to n greater than 1 into two parts. A1 equal to set n belongs to n greater than n1, xn belongs to I1 dash. B1 equal to set n belongs to n greater than n1, xn belongs to I1 double dash. If A1 is infinite, we take I2 equal to I1 dash and let n2 be the smallest natural number in A1. By the well ordering property of n, every non-empty subset of n has a least element, hence A1 must have a least element. If A1 is a finite set, then B1 must be infinite, and we take I2 equal to I1 double dash, and let n2 be the smallest natural number in B1. We now bisect I2 into two equal subintervals I2 dash and I2 double dash and divide the set n belongs to n greater than n2 into two parts. A2 is equal to set of all n belongs to n greater than n2 x n belongs to I2 dash. B2 is equal to set of all n belongs to n greater than n2 x n belongs to I2 double dash. If A2 is infinite, we take I3 equal to I2 dash and let n3 be the smallest natural number in A2. If A2 is a finite set, then B2 must be infinite, and we take I3 equal to I2 double dash and let n3 be the smallest natural number in B2. We continue in this way to obtain a sequence of nested intervals I1 superset of I2 superset of etc. superset of Ik superset of etc. and a subsequence xnk of x such that xnk belongs to Ik for k belongs to n. Since the length of Ik is equal to b minus a by 2 raised to k minus 1 and since infimum of the set b minus a by 2 raised to k minus 1 k belongs to n equal to 0, it follows that there is a unique common point psi belongs to Ik for all k belongs to n. Moreover, since xnk and psi both belongs to Ik, we have modulus of xnk minus psi less than or equal to b minus a by 2 raised to k minus 1. Whence it follows that the subsequence xnk of x converges to psi. A bounded sequence can have various subsequences converging to different limits. For example, the sequence minus 1 raised to n has subsequences that converge to minus 1 and other subsequences that converge to plus 1. It also has subsequences that do not converge. For example, the sequence itself is not convergent. Let x be a sequence of real numbers and let x dash be a subsequence of x. Then x dash is a sequence in its own right, and so it has subsequences. We note that if x double dash is a subsequence of x dash, then it is also a subsequence of x. Theorem 5. Let x equal to sequence xn be a bounded sequence of real numbers and let x belongs to R have the property that every convergent subsequence of x converges to x. Then the sequence x converges to x. Proof. Suppose m greater than 0 is a bound for the sequence x equal to sequence xn, so that modulus of xn less than or equal to m for all n belongs to n. Suppose also that the sequence x does not converge to x. It follows from theorem 2 that there exists an epsilon naught greater than 0 and a subsequence x dash is equal to xnk of x such that modulus of xnk minus x greater than or equal to epsilon naught for all k belongs to n. Equation number 1. Since x dash is a subsequence of x, it follows that m is also a bound for x dash. Hence, it follows from the Bolzano-Weierstrass theorem that x dash has a convergent subsequence x double dash. As we have noted, x double dash is also a subsequence of x. Hence, it converges to x by hypothesis. Consequently, it ultimately belongs to the epsilon naught neighborhood of x. Since every term of x double dash is also a term of x dash, this gives us a contradiction to equation number 1. Now, let us summarize this session. In this session, we have described the notion of a subsequence of a sequence of real numbers. We have stated Bolzano-Weierstrass theorem and gave 2 proofs for the same. Before moving to the next session, try to answer the following questions. 1. Let x equal to sequence xn and y equal to sequence yn be given sequences, and let the shuffled sequence z equal to zn be defined by z1 equal to x1, z2 equal to y1, etc., z2n minus 1 equal to xn, z2n equal to yn, etc. Show that z is convergent if and only if x and y are convergent and limit x equal to limit y. 2. Suppose that every subsequence of x equal to xn has a subsequence that converges to 0. Show that limit x equal to 0. 3. Let xn be a bounded sequence and for each n belongs to n, let Sn equal to supremum of the set xk k greater than or equal to n and let S equal to infimum of the set Sn. Show that there exists a subsequence xn that converges to S. 4. Show that limit sequence 1 plus 1 by 2n raised to 3n equal to e raised to 3 by 2. Books for your reference are 1. T.M. Apostol, Mathematical Analysis, Narosa Publishing House, New Delhi, 1985. 2. R. R. Goldberg, Real Analysis, Oxford and IBH Publishing Company, New Delhi, 1970. 3. D. Somasundaram and B. Chowdhury, a first course in mathematical analysis, Narosa Publishing House, New Delhi, 1997. Hope you enjoyed this session. See you next time. Till then, goodbye.